Dear participants of ICMS 2024, now our plenary speaker, Professor Dr. Ekrem rector of Usak University, will deliver his talk. Here you are, Professor Savaş.
Okay, thank you. Good morning, everyone. And first of all, I would like to thank the organizing committee and the particularly Professor Huseyin Cakalli. Actually, he is doing the very well jobs every year organizing the conference. So he is the gathering the mathematicians to share their knowledge and their experiences. So today I will talk about the double sequence statistical, almost double statistical convergence by the combining the Euler Poisson. And actually, this is the title of my talk on new lambda double sequence spaces on the semi-enormous spaces. Everyone know that statistical convergence is as a generalization of the convergence. And the first time they considered by the FAS and Sprienen from the almost convergence. And during that time, Schoenberg also defined this one independently by FAS. Then they wrote the paper and denotes the set of natural number, K set of the N, and the K Mn denotes the cardinality of the K intersection Mn, and upper and the lower natural density of the subset of K defined like this way. If upper and lower natural density are equal, we say that this is natural density of the K exists, and it is denoted by usually dk. And clearly dk the limit k1 and is going to the infinity. And so we are defined the statistical convergence. There is the one sequences real numbers is said to be statistical convergent to L. For every epsilon greater than 0, this set has the natural density, there's 0. And usually we are expresses to write statistical limit xk equals 1. And also usually we are denoted this is by S. Later the FAS, many mathematicians consider the statistical convergence. And very important two papers that are here, Fidelity paper and the Salat, and also Jeff Connell paper. This is very important for the statistical convergence the considered. Fidelity, actually what he done, Fidelity, show that the concept of statistical convergence sequences and the statistical quotient sequences are shown to be equivalent. And also statistical convergence is the study as a regular summability method. This is very important because they are getting the link between the statistical convergence and the summability theory. And it is shown that it cannot be included by any matrix method. There are two Tauberian theorems proved by the Fidelity. One of them is the one uses the Tauberian conditions, which is shown to be best possible, and the other is concerned with the gap sequences and further proved the following theorems. This theorems is just I want to bigger, and he proved this theorem. This is very important theorem, and the following statements are equivalent. And one of them is X statistical convergence sequences. And the second one is the X is the statistical quotient. What happened? I'm sorry. Disappeared. I'm so sorry, just I'm coming. Just disappeared my pages. Okay, I'm so sorry. But no, it's second. Okay, and the third one, X sequences for which there is the convergence sequence Y, such that Xk equal to Yk almost all K. And he proved that next theorem, no matrix summability method can be included in the method of the statistical convergence. And also, he showed that by adding the different conditions to the statistical convergence, if X sequence is such that statistical limit Xk equal to L, and this condition is there, this is the bounded, and then this is the convergence. And the Salat, it is very important paper published in the 1990, and he presented that set of all bounded statistical convergence sequences nowhere dense subset of the linear norm spaces. Norm spaces L infinity. L infinity, this is the set of the bounded sequences, and this is the Banach spaces. And the set of the all statistical convergence sequence of real numbers is the dense subset of the first Bayer category in the fresh spaces. We denote by M0 the set of the all bounded statistical convergence sequences of real numbers. And he proved theorem the set M0 is the closed linear spaces, subspaces of the linear norm spaces, L infinitive. And the next theorem, the set M0 is the nowhere dense set in the L infinitive. By S0, the set of the statistical convergence sequence real numbers in what follows as denotes the fresh metric space of all real numbers, these sequences with the metric. And he proved the set S0 is the dense in the space of space S. And the next one, the set S0 is the set of to the first Bayer category in the spaces S. Later on, lambda as an extension of the statistical convergence, as lambda statistical convergence was given by Murselin. And he proved that the following theorem, and Xk is the convergence to L according to the de Laval Poisson, and that time this is a lambda statistical convergence, and this inclusion is a strict. And the next one, if X bounded sequences, that time this first inclusion turned the converse, and looks like Xk lambda statistical convergence, then Xk the de Laval Poisson convergence, and also the Cesaro convergence. And the third one is the equivalent to this if the infinity boundaries. And also he proved that the set of the statistical convergence set of subset of the lambda statistical convergence if and only if this condition is satisfied. And now I am going to the next pages. Can you open this? I think, but it's not coming. Third one. Okay. No. Second page. Can you second page? I think third one. This third. Yeah. Oh, okay. Now, throughout the paper, I will use this idea to define the lambda almost double statistical convergence of the weighted G. G is R plus time R plus to go to R plus, and G XMN goes to infinity when XMN in this here with the XMN is going to infinity. Throughout the paper, we will use this one. And now I can give some brief introduction about the double statistical double convergence. This is was given by the Prischheim, and the convergence of the double sequences I already mentioned. It was given by Prischheim. Double sequences XKL. The Prischheim has the Prischheim limit. Usually we are using this symbol to denote this one. And arbitrary epsilon greater than 0, there exists positive natural number xkl minus l less than infinitive, less than epsilon, I'm sorry, whenever the kl is greater than or equal to that. And we shall describe such as x, the Prinshine says, as a p conversion. Later on, many people consider the double sequence spaces. For example, Peterson and some others, the order. And also, for the double sequences, we can define the bounded sequences. A double sequences xkr is bounded if it is the less than infinitive. Usually, we are using this symbol L to infinitive to denote the bounded double sequences, and C to infinitive set of to the bounded and the convergent double sequences. So, and many people consider this one, and also, as we know that almost convergence for the single sequences was given by the Banach, and later on this was extended by the Lorentz. What about, you can think about, what about for the double sequence spaces? This has given by the Hill. Hill defined that a linear functional L is said to be Banach limit if has the following properties. The first one is it should be the positive, and the third one LE equal to the 1. The E is the sequence EKL, usually EKL equal to the 1 for all L, and the third one is the Lx equal to the L. This is the shifted for the double sequence spaces S1 0 and 0 1 and S1 1 1. So what is the means? S01 xk, the first term of sequence is the shifted, as the 0 1, this is the second term is the shifted, and S11 both terms is shifted. So this was given by the Hill, and B2, the set of the all bounded limits, Banach limit of L infinitive, and we are using this symbol, and the double sequences xkl is said to be almost convergent to the number L if all the Banach limits coincide. By following Lorentz, Morris and the Rose define almost convergent for the double sequences as follows. They consider the xkl the almost convergent to the L if this limit is axis and equal to the 0. The first time they defined this one by following the Lorentz. And also they characterize that C2 hat, this is the almost convergence double sequences set, this one, and this limited axis equal to the equal to the 0 uniformly in P and the Q, and the TKL PQ defined like this way. And if double sequences is the called strongly double almost convergent to the number L if this limit axis and equal to the 0 uniformly in the PQ. Usually it is it's easy to see that, and this set is sub of this set and a sub of this set and sub of this bounded the almost convergent sequences, and also the strictly. Later on, what happened? Mursalen extended first definition by using the double sequences, and he defined that statistical convergence for the double sequences. A double sequences xkl is said to be statistical convergent to L, provided that for each epsilon greater than 0, and this limit is axis and equal to the 0. If x statistical convergent, then x not to be convergent, as you know, and also it is not necessarily bounded. More recently, development on double sequences can be found under some other references. And also lambda and the lambda n, mu and mu m, two non-decreasing sequences of positive real numbers, and both of them is going to the infinitive. And also they satisfy this condition, lambda 1 1, and this condition also mu 1 equal to the 1. This is one kind of next page. So they find the Euler poison for the double sequences. And usually a double sequence is said to be there's a Euler small to the number L if this limited access and the convergence to L as nm goes to infinity in the Prinsham set. Throughout the paper, we will consider lambda n times m by this symbol, and I belongs to the IN, G belongs to the IM. We consider this one KL INM. So we define now our definition. Lambda and lambda m real numbers, which one defined before, and X seminorm spaces with the seminorm Q, and V as the sequence, all sequences S equal to the SKL, and SK is belongs to the seminorm. If, I'm sorry, this is the SK, this is the SK, a sequence is SKL, lambda double almost statistical convergence to weighted G, if there is a complex number as such that this limited axis and equal to 0, uniformly in PQ. Here, lambda n or real numbers is defined, as you know, that we defined it before. And usually we are using to demonstrate this symbol with this one. And throughout this paper, the set of the lambda q double almost statistical convergence sequence of weighted G will be denoted this symbol. Now, if I take G n m equal to this one, alpha between the 1 and m, I can get the lambda q double almost statistical convergence of alpha, and the lambda nm equal to the nm. That time GNM equal to the NM, alpha equal to 1. I can get the notion of the double Q almost statistical convergence. This is the particular case, our definitions. And we are using the symbol just to denote the sequence, the double Q almost statistical convergence sequences as Q hat. And we proved the following theorem. Next page. We prove the next theorem. G belongs to the capital G and SKL and the complex number. And if this sequence spaces convergence to the lambda, double lambda statistical convergence to the S0, and C is the complex number, that time we can get this one. And the next one, this is if this sequence SKLs, the sequence double sequence SKL, the convergence, double lambda statistical convergence, Q convergence to the X0, and also RKL, this sequence spaces convergence to S0. That time there are summation, also the convergence to S0, the plus to the S0. And the next definition, X is seminorm spaces, and the Q and the WS with the space of all sequences XK, L, this is the by mistake, where SKL XX, T the positive real number, and this is this sequence spaces strongly double almost summable to weighted G if there is the complex number L such that is limited axis and equal to the 0. So uniform in PQ. The set of strongly these double almost statistical sequences will be denoted by this symbol. And also it's possible to get the particular case here. And we prove that this theorem there is the weighted one G1 and the weighted G2, and there is axis the M0. There is the U and Y belongs to the n times n such that satisfies this condition for all n greater than the equal to the U and the m greater than the equal to Y. That time this is the subset of the subset. And also we can get to the particular cases. If I take only one G belongs to the G, and also there is there exists the M0 greater than 0, it is possible the same satisfies this condition, and that time I am getting this subset of this one. So another one, if this set is subset of this set if this condition is satisfied. So if I satisfy this condition, I can get the inclusion theorem. And the next theorem also, it is similar that the previous one. There is the two weighted G1 and G2, and the G1 and G2 satisfies these conditions for all n and for all m, and that time this sequence space is subset of the sequence spaces. And also looks like the corollary 3.7, we can get the 3.10, the same, the inclusion. And the next one also, which is possible to that, T and U between the 0 and infinitive, and G belongs to the capital G. That time, this is a subset of this one. This is the easily to get by using the Holder inequalities. And this part, it's very important theorem. This theorem, this is if sequences SKL strongly almost double summable of the weighted G1 to L, and that time lambda almost double statistical convergence of weighted G2 to L. This means this is the subset of this one. And also particular case, it is possible to get for the theorem 3.12. And the next theorem, next part, I will define the new sequence spaces, and I will get to some inclusion theorem to finish this paper. And in this part, I will consider the Euler's function. Euler's function, as you know, that one kind of the functions, the more than the modulus function, but it is the defined by inspiring the modulus function, and more general than the modulus function. And this Euler's function, this is the from the R plus to R plus, is a continuous convergent non-decreasing function such that m0 equal to 0, mx greater than 0, for x greater than 0, and mx infinitive converges infinitive when x converges to the infinitive. Is the later stage different class of Euler's function, different order? Consider this one. Recently, this considered by the Prasha and Chaudhary, and also I consider the many papers by using the Euler's function. Euler's function, I define here one sequence spaces by considering Euler's function. M is Euler's function. T and T, L, this is sequences of strictly positive real numbers. And G belongs to the G, and X semi-normal spaces. And these sequences is we define the following definitions. This sequence spaces, actually this is this limited axis and equal to the 0 for some n, and the rho greater than the 0. And if X belongs to the here, I can say that, X is strongly double lambda almost summable of the weighted G with respect to the Euler's function M. If we consider what is assignment of M, lambda, and T, then our definition will be reduced to the different particular cases. I'm sorry. Yeah, if I take the particular cases, the first one, if I take mx equal to the x is the positive, lambda nm equal to the nm, tkl equal to the 1 for all k and l, and that time my sequence spaces will be reduced to these sequence spaces. In here, in my definition, if I take the tkl equal to the 1, and that time my sequence spaces this reduced to the sequence spaces. And the tkl1 equal to the 1 for all kn, lambda nm is nm, and that time my sequence spaces reduced to this sequence spaces. If I take lambda nm, and that time this sequence spaces reduced to this sequence spaces. So it is possible to get different part of the particular cases from my sequence spaces. This is the new sequence spaces. Now I will get to some theorem from here, but I just remind that throughout to the here, this is the KL should be the sequences is bounded, and it should be condition satisfied. This condition satisfied. So now I can give now another theorem. G1 and G2 belongs to the G. Their axes are greater than 0, and U0 and W0 belongs to here. And G1 and G2 satisfies these conditions, and M is the oldest function, and that time we are getting that this is subset of this sequence spaces. And in the next part, I will get to the inverse part of this theorem. Inverse part of the theorem. How the oldest function is the oldest function, but this sequence is the bounded. SKL is bounded. If the sequence is bounded, so I can get to the inverse part of the first theorem, theorem 3.15. So what happened here? I can get it to the weighted G1 and G2, and R is positive sequences. This is the n times n, and this weightedness satisfies this condition. Sorry. Oh. Yeah. I'm sorry. This okay. And that M is the oldest function, as K is the bounded, and that time it is possible to get this condition. But meanwhile, the previous theorem, I get it to the inverse part, this theorem. Look at here, look at here. Yeah, I get to this one, but the next theorem is I get to the inverse one. So, and finally, I get to the complete of my paper, but I will mention some important. There is some important results here. One of them, there are some papers here that is very important. I mentioned the first paper, the definition of the statistical convergence, and fifth paper is very important for the statistical convergence between the summability theory. And Hardy also, the Hill defined the almost convergence for the double sequences. And some people used to define the sequence spaces by order alpha 0, and between 0 and 1. Our results more general than order alpha, because I used to use the weighted G. The order alpha is a particular case by the result. And also this paper is a very important, Mursalen, and this paper, this is the one part, the lambda statistical convergence. This is the generalization of the statistical convergence, which must be defined by the Mursalen, and later on, the many people use the lambda statistical convergence as a generalization of the lambda statistical convergence. And also for the double sequences, Mursal and Adli defined the statistical convergence. They published this paper, JMAA. And also there is some other paper, Peterson paper for double sequence spaces. And also I used to do the different sequence to create some different sequences by using the Orlo's function, as you see here. That is I completed my talk, so thank you very much for your attention. Cakalli? Yeah. Oh, come here. Okay. Geri gelsene, yanlış oldu.
Sesinizi açın hocam.
Thank you for your talk, Professor Ekrem Savaş. Is there any question? Either face-to-face participant or online participants? No. Thank you again.
Thank you. Thank you very much. See you again. Thank you.
See you again.
I wish you all of good luck. Happy day.
No, thank you.